Section 8.3, Atomic Spectroscopy and the Bohr model. So when atoms or molecules absorb energy, that energy is often released later as light energy. And examples of this you've probably seen are fireworks and neon lights. So these are element lamps. This lamp has mercury in it, this one has helium, and this one has hydrogen in it. And it's very similar to how neon lamps work. So there's a gas inside the tube, and a high electrical voltage is applied across the tube, which gives energy in the form of electricity to the gas, and then that releases the energy in the form of light. And so the color of the light is distinctive of the element. So this is a neon light, a neon sign, and that's the color that neon gives off. And all those beautiful colors in the fireworks are from different elements, absorbing energy from the explosion and then releasing that as light. If we take the light that's emitted from atoms and molecules and pass it through a prism, we see a very specific pattern of wavelengths. It's not a continuous rainbow like we see with sunlight. It's called an emission spectrum, and it's specific for each element or compound. It's not continuous, meaning there are bright lines and dark spaces, and you can use it to identify something. It's a lot like a fingerprint or a barcode. Classical physics cannot explain why elements and compounds do this. So this is the setup here. So here we have, this is a hydrogen lamp, and it's giving off kind of a pinkish light. And we'll filter it through this slit to just select some of it, pass it through a prism, and instead of getting a continuous rainbow, what we see are three distinct lines. And the colors of those lines are always the same, and the wavelengths can be measured. So that's what the hydrogen spectrum looks like. This is helium and barium. This is what you expect to see with sunlight. For oxygen and neon, which are more complicated, you're going to have a lot more lines present. So this is what we just looked at, an emission spectrum, where you're zapping the atoms and they release the energy back as light. You can also throw light at the atoms and see what they absorb. And so here we're looking at dark spaces. Those frequencies or wavelengths of light do not get transmitted because they get absorbed by mercury. We can identify some elements by the color of their flame tests. And again, this is related to the color of light that they emit. So sodium gives this bright orange-yellow flame. And that's a common color that you see in fire, right? Because there's sodium everywhere. So you'll see this color in a wood-burning flame. Potassium is this pretty green color. Lithium is red. Barium has this kind of greenish color. The color that we're seeing here is the combination of the particular wavelengths of light that element emits. So it's a little bit like mixing paint, right? If you have blue and yellow and you mix them together, you get green. And so the green appearance here, there's probably some blue light and some yellow light involved, possibly as well as green light. But it's a combination of all the different wavelengths. So a guy named Johannes Rydberg, back in the 1800s, analyzed a whole bunch of these atomic spectra and was trying to figure out a way to describe them mathematically. And he did come up with an equation, which is really cool, although it doesn't really give us any insight into what's going on. So this is his equation. And I like it better this way. 1 over the wavelength is equal to R times 1 over m squared minus 1 over n squared. So that works to describe the relationship of the wavelength and that you observe, and they are factors of different integers. Doesn't explain anything, though. So Rutherford's model of the atom had the nucleus at the center, very tiny, very dense, almost all the mass, and that was positively charged. So the nucleus has the protons and the neutrons in it. And then the positive charge on the nucleus is balanced by negative charge of electrons, and those electrons are moving around in the empty space surrounding the nucleus. He didn't know what they were doing. Turns out that was a really hard thing to figure out. So the problems with this model are that electrons are charged particles, and according to classical physics, if you have a moving charged particle, that should be giving off energy, which means it's going to be losing energy, right? And it should eventually crash. Stop. We also would expect to be able to detect that energy, and the atoms should basically glow, but they don't. So the nuclear model doesn't explain what happens in the atom when it gains or loses energy. So that was a deficiency of Rutherford's model. Niels Bohr, late 1800s through 1962, he developed a model of an atom that does explain what happens when it undergoes energy transitions. So in Bohr's model, the electrons are traveling around the nucleus in circular orbits, much like the planets orbit around the sun, right? So you've got the sun, think of the solar system, you learned about this in school, there's the sun in the middle, and then there's the planets, and they're going around in their orbits, right? So this was a lot like Bohr's model. The nucleus was the sun, and the elements are the planets. Those orbits are only at specific distances from the nucleus. We don't have a planet between Earth and Mars, right? There's not one in there. So in this model, the energy of those orbits are quantized. Each orbit has a fixed amount of energy, and the amount of energy in the total atom is related to the energy that all the electrons have. And this word quantized means that there are only particular values are allowed. Quantized as opposed to continuous. And I'll talk more about that in a minute. So here's part of a diagram, you can imagine it just continuing around, of the Bohr model. So here we have the nucleus, like the sun, and then we have these different orbits that electrons can be in. We see this emission of electromagnetic radiation of light when an electron moves from a higher energy orbital to a lower energy orbital. Energy is conserved. If the electron loses energy, the energy has to go somewhere. Here it's emitted as electromagnetic radiation, and some of these transitions have an energy that corresponds to visible light. So one electron moving from here to here would emit one photon of light, one piece of light. The distance between the orbitals is related to the amount of energy, which is related to the wavelength of the photon produced. Any questions yet? So we've talked a little bit about how the very small things, quantum-sized things, behave very strangely. Right? We talked about Schrodinger's cat and some other weird things. So the electron is never observed between states. It's in one orbit or it's in another orbit. And when it moves, it makes a quantum leap, meaning it moves from that one orbit to the other orbit without going through the space in between. And if that seems impossible, then you're thinking correctly. That does sound impossible. And this quantum leap is the name of a TV show, right? It's an old show. They've remade it. Making new episodes. It's pretty good if you haven't seen it. But in that show, the quantum leap is this guy is in one place in space and time, and then he leaps and he's in another physical place and another physical time. But he doesn't go through space and time. It's just like you're here and they're there, which if you're thinking in terms of particles is not possible. Particles can't do that, but waves can. So the energy of the photon that's emitted is the difference between those two stationary states. And those energy states can be calculated because we can measure the wavelength of the light that's emitted, and from its wavelength we can calculate its energy. So then we can see that the energy difference between these two states is such and such a value. So the Bohr model has great historical and conceptual importance. Of all the models of the atom, it's one of the easiest to think about, and there is still some use in kind of thinking about the atom as being like the Bohr model, as long as we understand that it isn't really. But we've got the nucleus in the middle, and we've got the electrons going around in orbits like the planets, right? But unfortunately, the Bohr model only works for hydrogen with one electron, so that makes it really not very useful. So it was replaced by the more complicated and complete quantum mechanical model.